All right, guys, section 2.2 for pre-calc. Need to talk about quite a bit of information today. This one I'm hoping isn't going to be too long, but here goes. Hoping isn't going to be too long for your sake, not mine. Okay, degree is the biggest exponent. It's also going to be the number of zeros that your graph potentially has, okay, whether they're real or non-real. The leading coefficient is the coefficient on the term with the largest exponent, or the biggest exponent, so I use the same verbiage as back up here. It controls which quadrants the graph is in. So, for examples, this graph, or this equation, is degree 2, because it's the biggest exponent, and the leading coefficient is -2. So the leading coefficient is -2. So as you guys know, because this is degree 2, it's going to be a parabola. And because the leading coefficient is negative, you know it's opening down. Well, the same thing is going to be true for other equations. That the degree is going to give you the shape of the graph. The degree told me it's a parabola, and the leading coefficient told me it's opening down. So all we have to do is know what the degree looks like. So this is a degree 3 with a negative leading coefficient. So the leading coefficient is -2. Okay, do we care that it's a -2? No, we just care that it's negative. That's all that's important. So it's not, the size right now isn't really important. Yes, the size does change the shape of it, but it's the fact that you're really just looking for, is it positive or is it negative? In other words, is it opening up or opening down? So in the next few pages, I'm going to show you how to know what the degree of an equation looks like as far as graphically. This one is going to have this general shape. Okay, I'll go through those, but that I knew was degree 2, so it was a parabola. This is degree 3, so it's going to have that general shape, and I'll talk you more through that. Okay, so a parabola. If you grab your graphing calculator and type it in, you're going to get a shape like this. X to the 4th. I'm sorry, let me back up. The degree of the function can be broken into 2 categories. It's either an even degree or an odd degree. So I've got all even degrees here, and I'm simplifying them by not having additional stuff added or subtracted from it. Just keep it simple. So apologize, I just jumped straight in. So I know that's a parabola. If you put it in your calculator and graph it, you see that. X to the 4th, what you're going to see is the sides are less curved, it's steeper and flatter at the bottom, and then comes up again. So for each degree, successively, the sides are going to get steeper and the bottom is going to get flatter and heading up. Okay? It's not going to get right angle like this, like I'm exaggerating here, but you get my point, that the parabola is nice and curved, the sides get steeper, flatter on the bottom, the larger the even degree is. Now notice the leading coefficient on these was all a +1. If they were all negative, like negative x to the 8th, then it's going to open down. Okay? And again, I'm exaggerating the graph by doing that. Okay? It doesn't really go right angle, but I'm just exaggerating to prove a point. Okay. Assuming that all of these are the ones with the positive leading coefficient, so I'll get rid of this one. The new terminology for you is we need to look at the left-hand end behavior and the right-hand end behavior. How it works is your answers are either going to be positive infinity or negative infinity, or what you're going to write in these blanks. Okay? How you approach it is, as the graph goes really far left, so the left-hand end of the graph, what are your y values doing? Well, they're going really high up. They're going towards infinity. So as you go towards the left, your y values are going towards infinity. On the right side, as you go really far right, your y values are going really far up, once again. So they're going to positive infinity. So all of these, for a positive leading coefficient, the left-hand end behavior and the right-hand end behavior are the same. In this case, they're both positive infinities. If your graph had a negative leading coefficient, like this one I gave a bit ago, automatically you know the left hand end behavior is going to be negative infinity, and the right hand end behavior is also going to be negative infinity, because your graph is going to be doing this. So as you go really far left, you're going down to negative infinity. As you're going really far right, you're also going down to negative infinity. The leading coefficient and the degree controls what the end behavior of the graph looks like. This is going to control the gross, the large scale, the macro, not micro, the macro shape of the graph. It's going to control the end behavior of the graph. So this graph, oops, sorry guys, I'm searching for the button, I know that's there. This one is the leading coefficient is -2 and the degree is 2. It's an even degree graph with a negative leading coefficient, so I know that generically it's going to look like this. So the left hand end behavior is going to be negative infinity. The right hand end behavior is also going to be negative infinity. This one, because it's degree 3, which I haven't talked about odd degree polynomials yet, so I'm going to hold on and come back to that in a minute. I just wanted to look at this one because it's a parabola, and we know how to deal with an even degree function now. Okay, coming back over here, scrolling down a bit. So this is degree 6, positive leading coefficient. So it should be written 4x to the 6th plus 3x to the 5th, blah, 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 blah. Okay? But sometimes they try and trick you and not put the biggest exponent, because that was the definition when you come back. It's the biggest exponent. Okay? That it's going to be shaped like one of these. Okay? It's going to be shaped like this. So, and the leading coefficient is positive, so the right and left hand end behaviors is the same as that. This one, it is written in standard form. It has an even degree negative leading coefficient, so it's going to look like this graph. So both the end behaviors are going to be negative infinity. The left and the right end behavior are negative infinity. Okay? Now, the formal way of writing this is a bit cumbersome. It goes, as x goes to negative infinity, f of x goes to, and then you write your answer there. As x goes to positive infinity, f of x goes to. Now, to translate this, it's all I'm doing is as you go really far left. That's what this says. And your y values do what? Because f of x are your y values. As you go really far left, your y's, well, how are they acting? As you go really far right, what are your y values doing? So I'm just trying to translate the formal way of saying that so you guys are a little more comfortable when you see that writing in the book. Okay? I'm doing it very conversationally, telling you how to approach it conversationally, but you also need to understand mathematically what the writing means. As x goes really far left, to negative infinity, f of x goes where? Your y values go where? That symbol just means goes to. How does it act? Okay? All right, a line with a positive leading coefficient just heads this direction. If it had a negative leading coefficient, it would be going down. Okay? This graph is going to come up, curve through the middle, and head up like that. It's not quite so steep here, but you know I'm writing with the slate. X to the 5th, it's going to be steeper and flatter in the middle and heading back out. Now I've exaggerated it once again, x to the 7th, just like I was exaggerating like x to the 8th as being very bucket-like. Okay? Sorry for that piece there. This is the same idea. I'm exaggerating it in the middle, okay, to be more flat. This, you know, the bigger the degree, the flatter it is in the middle. All right? What you'll see is the left and right hand end behavior for all these odd degree polynomials with a positive leading coefficient are the same. They're identical. The left-hand end behavior, as you go really far left, your y values go really far down. As you go really far right, your y values go really far up. They go high. All of these are going to act the same way. So an odd degree polynomial with a positive leading coefficient are all going to act the same way. There's going to be no difference between them as far as their end behavior is concerned. Now, what we haven't talked about is the more stuff that gets added to this, like an x squared, it looks like another plus, I apologize, minus x, so on and so on, or, plus x to the fourth, minus x cubed, blah, 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 blah. What that does to the graph is it makes it wiggle more in the middle. Now, I know I'm being really conversational about that, but that's what it does. But we don't care what's going on in the middle of the graph. We don't care what's going on in the middle. This is about the end behavior. What is the graph doing at the ends? And this stuff doesn't contribute to the end behavior of the graph. This is what controls the ends of the graph, the degree and the leading coefficient, the sign on the leading coefficient. If you add negative x to the fifth, then it's going to look like this. Negative x to the first, then your graph is going like this. As you read from left to right, it's going down to the right. Okay? All act the same way. So looking at this, the degree, whoops, I've got mistaken equations. These are the same equations as on the previous page. Well, I'm going to have to change that. So how about, for the sake of arguments for right now, I get rid of this. Okay? This would be an odd degree positive leading coefficient, so the gross shape is this. So the left-hand end behavior is going to be negative infinity. The right-hand end behavior is going to be positive infinity. This one, how about we change this to a 5? Apologize for my mistake. Its gross shape is going to be this. So its left-hand end behavior is going to be positive infinity. As you go really far left, the graph is going really far up. So positive infinity. The right-hand end behavior, as you go really far right, your graph is going really far down. So it would be negative infinity. And whether it's an even degree or odd degree, this is read the same way. As x goes to negative infinity, as x goes really far left, f of x goes to, your y values go where? And that's the question. That's what you're writing in there. A positive infinity or a negative infinity. Okay? It's always going to be one of those two words. Okay. Finding zeros. Zeros, if the zeros are real, mean they don't involve I, then they're the same thing as x-intercepts. Okay? But either way, you find your zeros by letting the equation be 0, equal to 0. Okay? One way you guys could do this is you could factor it. Because the leading coefficient is 1, I can ask what multiplies to 8 and adds to 6. Well, 2 and 4. That's supposed to be a 4. Now you set these equal to 0. So x plus 2 equals 0, and x plus 4 equals 0. I'm setting them equal to 0 because it's equal to 0. So x is equal to negative 2 and negative 4. Now, you guys could also do the quadratic formula, but I think you would both agree that for one like this, quadratic formula is going to be a lot more work than the thing is worth. Okay? You can just factor it. Always look to see if you've got something in common. In this case, you've got an x in common. Factor that x out of the whole thing. X squared plus 6x plus 8. So this would factor x plus 2, x plus 4, just like it did in the previous equation. It still equals 0, so now you're going to set all three pieces equal to 0. X is equal to 0, x plus 2 is equal to 0, and x plus 4 is equal to 0, and solve them all. So you're going to have 3 answers. Notice the degree is 3, you have 3 answers. The degree is 2, you have 2 answers. Okay? Factoring when the leading coefficient isn't 1. Okay, it's a little bit harder, but I'd still like you guys to be good at factoring and not just automatically reach for the quadratic formula. When you FOILed whatever it was that this was factored to get that, the first 2 things had to multiply to give you a 2x squared. So you know you need a 2x and an x. The end, the L's, multiplied to give you negative 20. Sure, you could have negative 1 and 20, 1 and negative 20. Sure. Yep, but it's rarely going to ever be those. 2 and 10, yeah, it could be. Most likely, it's going to be the 4 and the 5. Most likely. Okay? I'm not saying I'm guaranteeing that. I'm just saying it's most likely going to be it. So let's try 5 and 4. And there it is there. And now all we have to do is worry about the signs. Okay, so it's multiplying to negative 20. So 1's plus, 1's minus. Now do the O and the I of FOIL outside. Minus 8x. Say outside, inside, plus 5x. Notice I got a negative 3x and I have a positive 3x here. So that doesn't mean that I made a mistake. It just means that on my first guess, I just need to go back and change the signs. So this would be minus and this would be plus. So plus 8x minus 5x is a positive 3x. This thing is set equal to 0. So I'm going to take those pieces, 2x minus 5 equals 0, and x plus 4 equals 0, and solve them. So x is equal to 5 halves and negative 4. Once again on this, look for something in common between them all. There's an x squared in common. So then you have 2x squared plus 3x minus 20. I just did all the work before to factor in that one. So you start out with x squared equals 0. Then you'd have a 2x minus 5 equals 0. And an x plus 4 equals 0. So there are 4 answers. I know it's not going to look like it. When you square root this, you're only going to get 1. We'll talk more about that in a bit. It's called a double 0. I know it doesn't look like it's 2 different numbers, but technically it's 0, 0, 5 halves, and negative 4. But when you repeat, you only have to list it once. I'm just telling you that it is actually 4. The degree is 4. I'm not making this up. I'll show you what the graph looks like, and we'll talk more about the double zeros as we move through this. Okay. Factors, zeros, and factors. Given these factors, what are the zeros? Well, if I'm asking for the zeros and I got the factor, I think I'm tongue-tied. When I give you the factors and ask for the zeros, you're setting each of these equal to 0, just like we had just done in the previous problems. Okay? And you solve what they are. So that shouldn't be any big surprise. So if I give you the factors, that's how you find the zeros. Okay? Elementary, you got it. You don't need me to do it. I hope so. 5x plus 1 is equal to 0. Now you solve them. So x is equal to negative 1/5. X is equal to 3 halves. And likewise up above. Okay? Now, if I give you the zeros and ask for the factors, what do? Well, let's just back up. Notice here, your answer is 3 halves. And this is what it came from. The denominator is the coefficient, and this is the number in the back. And notice it's a positive, but it's negative. Look at this one. Minus 1, it came as positive 1. 5, it comes in front. So any number in the denominator is a coefficient. Any number in the numerator is read opposite of what's here. So 0 would be x, 2 would be x minus 2, and 7 would be x minus 7. So then this one would be x minus 2, x plus 5, and x minus 4. And if I gave you a square root, no big deal. X minus the square root of 3, x plus the square root of 3. Okay? Now, how do you multiply these out? Personally, I would FOIL that first. So I'd have x times x squared minus 9x plus 14. So then your final answer is x cubed minus 9x squared plus 14x. This one, I'd multiply two of them first. So x squared, and all I'm doing is FOILing it. Okay, I'm doing it in one step though. I'm doing it in my head as I go. So x squared plus 5x minus 2x, so that would be plus 3x minus 10. And then you still have to multiply it by x minus 4. Y'all can do the distributive property and bring stuff together. Sometimes I really like drawing a box for it. Some of y'all like the box, some of y'all hate the box. If you hate it, by all means, don't do it. I'm never going to require you to do it. But you'll see in some of these problems, it's really going to pay off. Okay, and I'll show you those on the next page. X and minus 4. And then you go through and you fill out the box. So that's going to be x cubed. I'm multiplying here. 3x squared minus 10x. And the thing about that I like about it is that, whoops, that's a 4, is that you know when you're done. So minus 12x and then 40. And now you just collect like terms, and usually diagonals are like terms. So your answer is x cubed minus 1x squared, because that was a minus 4, minus 22x plus 40. So that would be your final answer for this. Okay, the next one, if you need to, FOIL it. Okay, so that would be x squared, then plus the square root of 3x minus the square root of 3x, which you see cancel out. And then square root of 3 times the square root of 3 is 3, but one's positive, one's negative, so minus 3. So x squared minus 3 would be your final answer. Okay, I think this is the last screen. You need to be really careful when you do these, you guys. It is, let me try this again. If we had 2 and 3 as the zeros, you'd write x minus 2, and I'm going to exaggerate this, x minus, and then I'm going to fill this number in. If there was a coefficient with it, like 3/2, I'm still going to write x minus, but the denominator goes in front, and this number goes in the back. Okay? Now, this is 2 plus the square root of 3, and 2 minus the square root of 3. So you guys need to be careful when you write these out. X minus and x minus. And in there, I'm going to fill these two terms. Now, I'm going to be a little bit careful. I'm going to put parentheses. 2 plus the square root of 3 and 2 minus the square root of 3. So I've got x minus 2 minus the square root of 3 and x minus 2 plus the square root of 3. Yeah, this to me is when the box really comes in handy. Okay? I'm going to draw a box. It's going to be 3 by 3. Again, sorry for the squiggliness of all this. You'd think I was drinking gobs of caffeine or something. Maybe I should. Maybe that will smooth it out. Okay, I'll have to try that for the next one. All right, x minus 2 plus the square root of 3. So I wrote this one along the top, this one along the side. Does it matter which one goes where? Nope, absolutely not. And then I'm just going to multiply these things together. So this is x squared minus 2x minus the square root of 3x, and then minus 2x. That would be 4. That would be plus 2 square roots of 3. Then you've got square root of 3x. You've got minus 2 square roots of 3. And then you've got minus 3. So once again, the thing I like about doing the box is you know when you're finished. You know when you've multiplied everything together, it organized it. Now, some of y'all are a little more organized than I am, and if you want to just do the distributive property, that's fine. So the answer to this is x squared minus 4x. The minus square root of 3x and the square root of 3x cancel. The minus 2 square root of 3 and 2 square roots of 3 cancel out, and you're left with plus 1. So, given those two zeros, this is the polynomial that generated it. If I give you three numbers, then it's going to be 5, x minus 5 times x minus 2 minus the square root of 3, and x minus 2 plus the square root of 3. I would strongly recommend that you multiply those together first, like we did here. So then you get x minus 5 times x cubed, got carried away, x squared minus 4x plus 1. And if it was me, I would draw a box and multiply those together. Okay? I think you guys can handle, I'm not going to actually multiply the thing out because I think you guys get the gist of it. So x minus 5, x squared minus 4x plus 1. Multiply it together, collect like terms. Okay? And I think that's the last screen. Yep. So away you go. Have yourself a good one, you guys.